So today we're going to start Chapter 4 in Schroeder's Thermal Physics book. I'm also using some resources from Thompson Higher Education to talk about heat engines and heat pumps. So let's get started with the definition. A heat engine is a device that takes in energy by heat and operates in a cycle. And when it operates in that cycle, it takes in the energy by heat, but it has to expel a portion of that energy that it takes in as waste heat to a cold reservoir. The rest of the energy goes into doing the useful work of the engine. So basically, all heat engines are carrying some kind of working substance through a cyclical process. Lots of times in power plants, for example, that might be steam, okay? In Otto cycle engines, it's a mixture of gas and fuel, but whatever it is, it's taking it through that cyclic process. So here's a little schematic of a heat engine. Basically, you have a hot reservoir, and it's sitting at some temperature we'll call T sub H, and the engine absorbs that heat energy. You can see that red arrow indicating that the heat energy Q sub H goes into that engine, and then a portion of that heat energy is converted into useful work, the work done by the engine. Okay, so that energy is leaving the engine. Also leaving the engine is the waste heat Q sub C, is indicated by the blue arrow, which is going to the cold reservoir. Now the cold reservoir is at a lower temperature, T sub C, compared to the hot reservoir. Oftentimes in, for example, Otto cycle engines, gasoline engines, the cold reservoir is just the air and atmosphere that surrounds us. Okay? Now, we discussed earlier when we were talking about the first law of thermodynamics that any change in the internal energy of a system is going to equal to the heat plus the work. So this is the first law of thermodynamics. Now, if something is being taken through a cycle, then it starts and ends back at the same point. If it's starting and ending back in the same point, then by definition, the change in internal energy between those 2 points is zero, because there's no change between those 2 points. And then that's equal to the heat plus the work. So what that means is that the net heat that is experienced is equal to the magnitude of the work done by the engine. These are magnitudes, okay? So any work done by the engine equals that net energy absorbed by the engine. We're going to use that to figure out what the efficiency is. So a thermal efficiency for a heat engine is defined as the ratio of the net work done by the engine during one cycle to the energy input from the hot reservoir at the higher temperature. So it's a ratio. Basically, you can think of it as a ratio of what you get to what you have to give. Okay, so what you get is the work of the engine, and what you have to give is that energy from the hot reservoir. So the efficiency E is then defined as the ratio of the work W divided by Q sub H, that magnitude. All right? Now, since the work of the engine by energy conservation is equal to QH minus QC, then the efficiency also is equal to QH minus QC over QH. Simplifying that expression, you can write your efficiency as 1 minus QC over QH. So you can write your efficiency a couple of ways there, and it just depends upon what variables the problem gives you as to which one of the formula is more useful. So thinking about efficiency, all heat engines expel only a fraction of that input energy Q sub H by mechanical work W. So their efficiency is always going to be less than 100%. In order for an efficiency to be 100%, you'd have to have that QC, that waste heat, be zero. Okay? And that's not possible. And this is summed up in another way of stating the second law of thermodynamics. This way is called the Kelvin-Planck form of the second law of thermodynamics. And it says that it's impossible to construct a heat engine that operates in a cycle and produces no effect other than the input of energy by heat from a reservoir and a performance of an equal amount of work. What they're saying is you're always going to have that waste heat Q sub C, and that can never equal to zero, which means there's never going to be an engine that has an efficiency of 100%, okay? And so there's no perfect engines. So another way of stating the second law of thermodynamics is there's no perfect engines. All right? Here would be a schematic of a perfect heat engine with Q sub C equal to 0. And that's impossible. It's not going to happen. So that's another way of stating the second law. Now, why are there no perfect engines? Well, The original way of stating the second law of thermodynamics says that the change in the entropy of the universe has to be greater or equal to 0. Okay? So the second law tells us that entropy for a process can only increase or stay the same. It can't decrease for any real process. So it's not only waste heat that gets dumped to the cold reservoir, it's also waste entropy, or at least you could think of it that way. So the entropy dumped to the cold reservoir has to be greater than the entropy drawn from the hot reservoir according to the second law of thermodynamics. Otherwise, delta S for the universe won't be greater than or equal to 0. So the Kelvin-Planck form of the second law of thermodynamics was actually discovered before entropy was understood. Carnot recognized in 1824 that there had to be a quantity associated with heat that flowed in through the hot reservoir and out through the cold reservoir in equal amounts if the engine was ideal. But of course there's no such thing as an ideal engine. It's only a theoretical construct, as we'll see in another lecture. It wasn't until Clausius's work in 1865 that the term entropy was actually coined. And that comes from the Greek word which means transformation. And Boltzmann really explained what entropy was in 1877. Okay, let me do an example problem for you. In this example problem, you have a heat engine that's connected to two energy reservoirs. One's a pool of molten aluminum at 660 degrees Celsius, and the other a block of solid mercury at minus 38.9 Celsius. The engine runs by freezing 1 gram of aluminum and melting 15 grams of mercury during each cycle. So if you looked it up in a table, the heat of fusion of aluminum is 3.97 times 10 to the 5th joules per kilogram, and the heat of fusion of mercury is 1.18 times 10 to the 4th joules per kilogram. So what's the efficiency of the engine? All right, so the way to solve this problem is to realize that the freezing and the melting is proportional to the heat, which is equal to plus or minus m times L, where L is the latent heat that was given in the explanation of the problem. So QH is going to be the mass times the latent heat, which for the aluminum was 0.001 kilograms times 3.97 times 10 to the 5th joules per kilogram. And that gives us 397 joules. The Q sub C, here we're only worried about the magnitude because our efficiency equation has an absolute value around QC over QH. So the magnitude of Q sub C is also equal to ml. The mass would be 0.015 kilograms times the latent heat, which is 1.18 times 10 to the 4th joules per kilogram. And that gives us 177 joules. So then the efficiency can be written as 1 minus Q sub C over Q sub H, absolute value, which is 1 minus 177 over 397. And that gives us 0.55, which means that the efficiency of that engine would be 55%. Okay, so that's some examples of heat engines. We'll get into more specific engines, specific examples of engines in another lecture. But for now, let's talk about heat pumps and refrigerators. So heat pumps and refrigerators are what happens when you run a heat engine in reverse. So this isn't a natural direction of energy transfer. Remember that if you put two things in thermal contact and one is hotter than the other, then the heat energy will spontaneously move from the hot to the cold, right? But you can force it to go the other way if you supply an input of energy. And that's what heat pumps and refrigerators do, okay? So a refrigerator is a common type of heat pump, and an air conditioner is another example of a heat pump. So here's the schematic of what's going on. Basically, instead of all the arrows for the QH and the QC going down and the work going out, the arrows flip and they go the other way. So now you're having to supply some useful work, usually in the form of electricity from the grid, right? So you have that useful work coming into the heat pump, and then you suck heat energy out of the cold reservoir, making it colder, and dump it to the hot reservoir, making the hot reservoir hotter. Okay, so that's the heat pump process. So for a fridge, what happens is the cold reservoir is on the inside, and you're trying to make the inside of your cold box or your refrigerator even colder, okay, or keep it cold. And the hot reservoir would then be the kitchen that the refrigerator is sitting in. And the kitchen gets a little hotter all the time, okay? So for an air conditioner, the cold reservoir would be inside your house and the hot reservoir would be outside because you're trying to make the inside of your house cooler. And if you want to run a heat pump to heat your home, then the hot reservoir would be inside the house and the cold reservoir would be outside. Now there's another way to state the second law, and this is called the Clausius form. The second law in this form states that it's impossible to construct a cyclical machine whose sole effect is to transfer energy continuously by heat from one object to another object at a higher temperature without doing work. Okay? So in other words, the work that you supply to the heat pump can't be zero for a heat pump or refrigerator. It's not possible. Another way to state that is energy doesn't transfer spontaneously by heat from a cold object to a hot object. It's not going to happen. Okay? So here would be a perfect heat pump, and you can see that there's no useful work coming in from the outside from the grid or anything like that. And you just have energy jumping magically from the cold reservoir to the hot reservoir, and that doesn't happen. Okay? So this is an impossible heat pump. Now, rather than using efficiencies to talk about heat pumps, instead we use what's called the coefficient of performance, or the COP for short. This is similar to the thermal efficiency for a heat engine. One of the big differences, though, is that your COP can be greater than 1, whereas your efficiency never can. Now, if you're running a heat pump in cooling mode, then what you really want is for the thing to be colder, right? So you're trying to figure out how much heat energy you can suck from that cold reservoir, all right? So all these numbers are basically what you get over what you have to give. So the COP for it in cooling mode would be what you get, which is the Q sub C, sucked from the cold reservoir, divided by what you give, which would be the work that the engine or that the heat pump has to receive. Okay, so it's Q sub C over W, and that gives you your coefficient of performance for something in cooling mode, like a refrigerator or an air conditioner. Now, a good refrigerator should have a high COP. Typical values could be maybe 5 or 6. If, however, you're using your heat pump to heat your home and not cool it, then what you get is Q sub H, not Q sub C. So your coefficient of performance for heating mode would be Q sub H over W. All right? So, yet again, the COP is generally higher, greater than 1, because Q sub H is typically higher than W. All right? I should note that if you're using a heat pump to heat your home, this is best in a moderate climate. If it gets really cold, it's not going to work so well, and we'll talk about why in a little bit. All right, here's how refrigerators and heat pumps actually work. So let's just look at a refrigerator. If you've ever stared at the back of your refrigerator, you might notice, if it's not covered very well, some coils on the back of the refrigerator. So heat pumps and refrigerators basically contain 2 sets of metal coils, and these coils exchange energy via heat with their surroundings. One set of coils is outside the fridge, and one set is inside. There's a fluid that's circulating through these coils. The fluid absorbs energy from the cold box and then releases it to the room. The fluid is cold and at low pressure inside the refrigerator, and it absorbs heat from the inside, further cooling the interior. And then, when the fluid moves out of the fridge, it's compressed to a higher pressure and it releases heat to the room. Okay, I hope you enjoyed that. We'll continue in the next lecture with a discussion of Carnot's cycle.